Welcome everyone to Deriving, derived state of explained. That was a very long title. I didn't think it would fit on this tiny little screen, so I derived an abbreviation. So last year I gave a talk called Opening the Shutter on Snapshots, kind of an introduction to the snapshot system, how state objects work and all that stuff. This is a bit of a follow-up to that. So my name is Klippenstein. I work on Jetpack Compose at Google. Let's get into it. So this is derivedStateOf. You might have seen it. And this is how it's defined. It takes a calculation function and gives you back a state that represents the result of that calculation. So you can use derivedStateOf to reduce invalidations when your inputs change more frequently than the output, and to cache expensive calculations that can be performed lazily. You should not be using derivedStateOf if you're doing cheap calculations and the output changes about as often as the inputs do. And I'll show you why. So the main thing to take away from this talk is don't use derivedStateOf unless you know you really should. So that's the talk. How am I doing on time? All right. All right. So the goal of this talk, for real, is to give you enough of an idea about how derivedStateOf works to help you know when you should use it and help you reason through some of the performance implications. So let's get started and look at some problems that derivedState solves. Got some fairly simple code here. We're creating two different mutable states, doing a calculation with them, and then spitting that out to the screen. So in this case, the calculation is cheap. You're just adding two numbers together, basically instant. And the result will probably change about as often as the inputs do. So this is not a good thing to use derivedStateOf for. You're just adding overhead. So to show this graphically, let's take a look at a not to scale graph, very not to scale. But we've got some calculation here that's cheap in blue. And we've got some rendering we're going to do. This is composition, layout, draw, all that stuff. We're going to do the calculation on every frame, and we're going to re-render it on every frame. So here, if we just add derived state to this, we're just adding the overhead of derived state in green, but we're not actually getting any savings anywhere. So that's bad. So let's look at a slightly different example. We go back to the code we just had, and let's change that calculation so now it's going to just basically return a Boolean that indicates whether the value is over a threshold or not. So now, for most of the values of the input states, the result's going to be the same thing. So we don't actually need to recompose foo here every time the inputs change, because most of the time, we're not actually going to be changing anything on screen. So this is where derivedState can be helpful. So we're going to wrap the calculation in a derivedStateOf. And because we're in a composable here, we also need to remember that. So now, the body of foo will only recompose when the result of this calculation actually changes. So if we look at our graph again, we've got our cheap calculation with the render every frame. But we don't actually need to re-render every frame because most of the time the result's not changing. So we add, I'm just going to flip through these. So we add the derived state. We get a little bit more overhead on that first frame. But most of the frames are actually doing less work because we'll do the calculation, we'll do the derived state of overhead, and but we won't actually re-render the frame. So that's good. That's probably a win. Third example. We've got a lazy column here with some items. And we want to sort the items before we display them. So we're going to call this expensive sorted method. This could be a long list, so sorting could take a while. But we're not actually going to use the result until layout. The item provider lambda that you pass the lazy column isn't actually called until the layout phase. So we don't actually need to do this sort in composition. But the way this code is written, that's what's going to happen. And then we're also going to use that sorted items to draw some decorations on top of or behind the items. So we're going to use the result again, but that's not going to happen until draw. So, well, one thing we could do here is wrap that call make it a function instead of just doing it right away. So we're going to remember a function that calls sorted, and then we're going to call that in layout and draw. So now we're not doing the calculation in composition. We're waiting until a later phase, but we're still doing the sorted calculation twice. So we're doing double work. So derivedStateOf again comes in to the rescue. we do the sorted call in a derived state of. So now it's lazy still. It won't be called until we first need it. Oh yeah, and there was one problem with that slide, which is that if you're going to have a derived state of, that's going to capture that items value. So you need to convert that items value into a state. And that's remember updated state is super helpful for this. Okay. Now the derived state of lambda is going to be reading that snapshot state, update.items, and it won't calculate until we need it in layout. So composition's fast, layout happens, we do the sort, and then we do the draw, and we don't need to recalculate we don't need to resort the list. We just reuse the sorted value from last time. So if we look at another graphical representation, we've got an expensive calculation in blue now, and more expensive than rendering. And so we're going to add derived state of. And in this case, we're still going to be rendering on every frame. Maybe we're scrolling the list. But we don't actually need to recalculate the result of the derived state every time. So that's indicated here with the blue. The calculation only happens now and then. And so if we go back, if you look at most of the frames, by not doing the calculation and just doing the derived state of and the render, we're still saving some time, except on those frames where we have to do everything. But that's also a win. So one kind of common anti-pattern I've seen a fair bit with this is having a composable function, takes some input, and returns a state. And inside there, you remember the input, but you're keying it off the input. So whatever you're remembering, it's going to recreate it every time that input changes. And then you're using derived state because you're like, well, I'm converting an input to an output, so maybe I'm doing some calculation with it, so I need to use derived state because it's more efficient. Well, you're also just capturing the input value. So what you're doing is every time the input changes, you're creating a new derived state and capturing the thing, doing the calculation again, returning it. The next time the input changes, you're going to create another derived state. So you're actually not really remembering anything interesting. You're just returning a new state object every time. And even if we, so basically what that is this code. There's no point in using derived state. You might as well just return the output every time. And all this is doing is, if the calculation is expensive, it's not going to run the calculation every time this method is called. But it's probably not what you meant to do. So, okay, so back to the bad example here. Probably what you intended by writing this code is to return the same state object that updates when the input changes. So to make that work, we have to take the key out of the remember. And this means that every time this is called in the same spot in the composition, it'll return the same state object. So we only create that derived state of one time. And now we just assume it's going to update. It won't update here, like I said a couple slides ago, because that derived state of lambda is just capturing that input value. It's not capturing a state that represents the input value, so we have to convert it to a state. And again, that's what remember updated state is for. So now every time this gets called with a new input, that updated input state is going to change. And then when the derived state of state object is read, if it needs to, it will reread that state and recalculate the output. So one more time, don't use derived state unless you know you should. Now let's look at how it works. So derived state of has two kind of main functionalities. The first thing it does is it can deduplicate invalidations. Like I said earlier, if your inputs change a lot, but the output doesn't change very often, you don't need to recompose or invalidate every time the inputs change. The other thing it does is it caches its result. So let's talk about invalidation first. What does invalidation mean? Well, invalidation is something that happens to a function in this case. And it means that we're going to mark the function as needing to rerun. So for example, a composable is needing to recompose. We're going to schedule it to eventually rerun in the future. So with composables, we're going to not recompose right away, but wait till the next frame. And then eventually we're going to actually run it again. So there's a couple of different types of functions or examples of functions that can do this. The first one, like I just said, is composable functions. But when you, and just one thing important to remember here, when you recompose a function that reads a state, the entire body of the function that read that state is going to rerun. So we're going to rerun the body of foo here, not just the text composable. And as you can see in this code here. It's because reading, if you read the state when you pass it to text, it's the same thing as reading it before, storing in a variable, and then passing it. So the read compose doesn't have any way to pass that value into text without rerunning the function body that passes it through. So not all composable functions, however, are invalidation scopes. If a composable returns a value that's not unit, it's not an invalidation scope, because the caller of that function needs to be called again in order to get the return value. So there's no point in rerunning a composable that returns something without rerunning the caller. And inline functions are also not invalidation scopes because an inline function just means that the body gets copied into its caller, so it's just part of the calling function. So some composables are invalidation scopes. Snapshot flow is another invalidation scope. When you read a state in the snapshot flow lambda, that lambda can restart when the state changes. There's a bunch of other functions in the compose APIs, layout, graphics layer, draw, stuff like that. Those will all also be invalidation scopes. So if you read a state in a graphics layer, for example, in the lambda form, and that state changes, only that graphics layer function is going to rerun. You're not going to recompose. You're not going to necessarily redraw. You're just going to rerun that graphics layer. And so that's more efficient than doing the whole pipeline. And all of these use something under the hood called snapshot state observer, which is just this kind of lower level API that helps take care of some of the logic for you here. And it's got this observe reads function, and that's actually what defines the invalidation scope. And then derivedStateOf itself. Its function is an invalidation scope because you can rerun that calculation function without rerunning anything that reads it. So to do this invalidation tracking, there's kind of two phases to it. First, we have to know what objects were read, and then we have to know later when they're actually changed. And then we go back and we can rerun it, and we'll keep track of what's read the second time and just rinse, repeat. So let's look at a little bit of a code example here. We're going to create two states. We're going to create a set that we'll use to track what objects changed. We're going to write a little function that reads a couple of states and prints out a value. We're going to wrap that in snapshot observe. And this is a function, a lower level snapshot API that takes this read observer. And the read observer is just called while the body of that observe is running whenever a state object is read. And the read observer gets past the state object itself. So we run this function. We're going to call state1.value. And when that getter is running, it's going to invoke the read observer. So we're going to add state1 to the read set. Then we're going to run state2.value. It's going to call the read observer again. And we're going to add that to the read set. Then we're going to print out the result. And we're done. All right, now that's the observing part, phase one. Now phase two, we gotta know when something changes later. This is what register apply observer does. So register apply observer gets called whenever a snapshot is applied to the global snapshot, and it gets past a set of all the state objects that were changed in that snapshot. So we're going to create a snapshot here, and we're going to change some states. When we change state one, the snapshot is going to track, okay, something changed state one inside in this snapshot. And change state two, it's going to track that as well. Then when we leave the with mutable snapshot block here, we're going to apply the snapshot, which is going to call the apply observer. And we're going to run this little logic, which is going to check to see if there's a match. And there is. So that means we need to invalidate. So we're going to schedule print results to run again. And at some point in the future, or maybe immediately in this case, we're going to call print result. We forgot one line here. We have to clear the read set because we're about to add to it again. And then we're going to run the code again, and we're going to print the result. Same result. All right. Well, we're not using derivedStateOf, so the fact that we just printed it twice, maybe that's why. So let's add derivedStateOf here and see if anything changes. We're going to wrap the calculation in derivedStateOf, and we're going to pull it out, so we're not creating a new one every time. And again, this is not a composable function here, and none of this code is actually composable functions. It's just using the snapshot stuff directly. And one quick note, the calculation doing here, adding two numbers together, like I said earlier, not something you typically want to use derivedStateOf for, but it's very simple and it makes it easy to run through the explanation. So just to keep things simple for the slides, we're going to do a simple calculation here. All right. So now we're going to call result.value. And when we read the derived state of, it's going to report itself as a state object that was read. Then it's going to have to say, OK, now I need to calculate my value. So I'm going to call the calculation function. It's going to read state 1. It's going to add state 1. It's going to report it to the read observer. Same thing for state 2. It's going to get reported. We're going to track it. And then we're going to return the result of the calculation, and we're done. Very similar to the first case, but now we're tracking 3 objects instead of just 2. We change the state again. We're going to do run this function. We're going to see there's a match. OK, we need to reinvalidate. So we're going to schedule print results. And we're going to run that again. And we've just printed out results again. Nothing special going on here. We saw something changed. We reran the code. So derived state on its own isn't doing the invalidation skipping. I said earlier, there's 2 phases to tracking validations. Knowing what's read, and then knowing when those things are changed. To skip or deduplicate invalidations, we need to add a few more phases. So we still need to know what state objects are read. But when a derived state is read, we need to know what its dependencies were. So the dependencies of a derived state are the state objects that are read in the calculation function. Then we need to remember what that derived state's calculation result was. And again, listen for when the objects are changed. And then when something's changed, instead of immediately invalidating, we're going to see, actually it was a derived state that was read. So I'm going to ask it for its new value. And only if the new value of the derived state changed will I validate myself. So derived state of is implemented as, when it runs, it tracks its own dependencies. And it has code to keep its own list. When you read from it, like in composition or something like that, that reader will ask the derived state. They'll say, oh, I'm reading a derived state now, not a normal state object. What other state objects did you read? And I'm going to track those instead of the derived state. Now, the only 2 invalidation scopes that do this are composition and snapshot state observer. Snapshot state observer, again, is the thing that's used inside of the layout lambdas and draw and all that. The reason for that is to do this, it requires calling some APIs that are currently internal. So you can actually make this work right now outside of the runtime library. But snapshot state observer is kind of like the public API for doing this. Most notably, snapshot flow does not dedupe invalidations in the same way because it doesn't really, it invalidates, when the state changes, it invalidates the actual function that you pass to the snapshot flow. But when that changes, it doesn't invalidate some other function, it just emits on a flow. So it uses much simpler logic, it does much less work, and just reruns its calculation, and only emits from the flow if something changes. So I'm going to run through an example here that applies to composition and snapshot state observer, but not snapshot flow. All right. We're going to wrap the calculation in a derived state of. I don't need to remember here because this isn't in a composable function. Then we're going to, inside the composable function, we're going to read the derived state value. So we're going to run the calculation and track that we read. The derived state of itself is going to track that it read these 2 states. Now the composable isn't tracking that it read the derived state because it doesn't actually need to write that down. Instead, what's going to happen is we're going to track that the derived state we just read had 2 dependencies. We're going to write those down. And then we're also going to track that those were read as part of a derived state. So we know which dependencies map to which derived state. We're going to track the result of that calculation as well. So foo, somewhere in the state of the composition, we know that foo read state 1 and state 2 as part of result, and results value was 0. So now we're going to go change our states again. We're going to keep track of those in the snapshot. And then when this applies, somewhere in the composition, it's going to use that, deep in the composition, it's going to use that register apply observer thing. And it's going to see that state 1 changed, and foo read state 1 transitively. OK, so it's going to say, I need a new frame, and on that frame, tell foo that it might need to recompose. The frame happens. The composition isn't going to recompose foo right away. It's going to instead look and say, OK, state 1 changed. And state 1 was read as part of result. OK, so now I can see what value result had the previous time. And I'm going to run the calculation again to see if it changed. In this case, it's going to be the same value. So we know that the derived state didn't actually change its result. So we don't need to recompose. So we're just going to skip foo. So we've skipped the complicated, the expensive thing of recomposing foo, and this is what we're actually trying to get to. So that's deduping invalidations. Now let's talk about caching. So this is a slide I showed earlier. And we've got our lazy column with some items that we're sorting and drawing a declaration. So before we talk about caching, we need to kind of understand how snapshots and state objects work. So this is where the talk I gave last year comes in handy. If you are watching the recording and you haven't seen this talk yet, I would strongly recommend pausing and going to watch it. But if you're in the room now and you haven't seen it, I'll just recap it really quick, and hopefully that'll be enough to understand what's going on. So snapshots are kind of like Git. A Git branch is kind of like a snapshot. Branches and snapshots are kind of isolated and independent from each other until they're merged. So you can make changes in one snapshot that no other snapshot's going to see. And when you merge it, then everything else will see it. Snapshots also have IDs. So we use that in state objects, so that when you're in a snapshot and you ask a state object for its value, the state object doesn't contain the value directly. Each state object has a set of records, and it puts its data in the records. Each record is tagged with the ID of the snapshot that wrote it. Each record can only be written by one snapshot. And once the snapshot is applied, or the branch is merged, then that record can't change again. So when you're in a snapshot and you ask a state object for its value, you're going to get a record. And different snapshots might see different records inside the state object. So that's how you get different versions of data in the same object. And the way that you select a record when you're reading it is you look for the record with the highest ID that's less than or equal to the current snapshot ID. And there's a few more rules here as well, but that's the most important rule for the caching implementation discussion. So if you want to know more about the things on this slide, go watch my talk from last year. DerivedStateOf is implemented as a custom state object. The calculation result and some metadata are stored per snapshot in the state records. So the caching happens per snapshot. It uses snapshot IDs and something called the snapshot write count to avoid recalculating the result, to know if it has to even try to recalculate the result. The algorithm looks like this. So when you ask a derived state for its value, we first check, has the calculation ever been ran? If it hasn't, well, then obviously we have to run it. If it's been run before, then we look at the current snapshot and our metadata and check, did we ask the derived state already for its result in this snapshot? If we did, has anything changed in the snapshot? Every time you write to a state object, there's this write counter that gets incremented in the snapshot. So we can tell, just by looking at that, if anything has been changed in the current snapshot. We don't know what yet, but we know if nothing's been changed, we don't even need to check. If something's been changed, or we're in a different snapshot, then we're going to check all of the dependencies, all of the state dependencies, and we're going to check if any of them have been written. And we can do that without actually looking at the state object values by just checking their record IDs. If we track all the record IDs from all the dependencies, if they're the same as last time, then we know that they haven't changed. And lastly, if at least one dependency has been changed since we last calculated the result, well, then we have to run the calculation function again and see if the result changed. So let's look through some code here. I might actually get through all these slides. All right, so we are creating our two states again. We've got a derived state, and we're just going to print out. We're going to start by just printing the value of the derived state. The snapshot table at the top here is going to represent the interesting data from the current snapshot. So in your actual code, when you're actually running this, there's a thread local that stores the current snapshot, and you can get it by calling snapshot.current. And you can ask the snapshot for its ID and its write count. And these are going to change as we go through this, so keep an eye on that table. So let's start by creating the first state. We're going to create a state record, or a state object, that's going to have a single record in it right now with the ID of the current snapshot, so ID 1. We're going to put the initial value into that record, 0. We're going to do that again for state 2. And then we're going to create the derived state object. Now, this is another state object, but it's record, and we're going to have record again with ID 1. But the record has a bit more data in it, so it's a bit bigger. It's got a value field, and it's got the snapshot ID and write count. And these correspond to the information from the current snapshot. All right, now we're not going to run that function right away. We're going to go ask derive for its value. So first of all, we're going to check that we've run the calculation before. We have the empty set over here, so it's a little flag that says, oh, we've never calculated this value before. All right, so we have to calculate it for the first time. So we're going to go run the calculation function. This is going to track, all right, I read state 1, and it's going to track that the record ID for state 1 was record 1. Then it's going to run state 2.value, record that it read state 2, and that it had record ID 1. So we're tracking dependencies here of the state object, of the derived state. The calculation is going to complete, give us a result, and we're going to write that down in the record as well. Now, before we return the value, we're going to advance the snapshot, and the reason for this will become apparent later. Advancing a snapshot is kind of a complicated process that I talked about in the previous thing, but for now, basically you can think of this as we increment the snapshot ID and reset the write count to 0. All right, so we've done that. Now we take those values and we track that in the cache. And this is for that part of the algorithm where we can check if we're in the same snapshot. So you can see there's a lot of data being stored in the derived state of already. Then we take the value and we return it and print it out. All right. Now, we've kind of read the derived state for the first time. All its fields are initialized. Let's do something a bit more interesting. We're going to create a new snapshot, which is going to mean it's going to have a higher ID. And we're going to do some reads and some writes. So we're going to read the derived state twice. We're going to change some values in such a way that the result is the same. Then we're going to try reading it again, and then we're going to change the result, and then read it one more time. And each of these is going to result in a different sequence of things happening. So we read the derived value for the first time in this snapshot. This time we're going to see, oh, we have a value in the cache. So we've run the calculation function at least once. Cool, so maybe we don't have to rerun anything. Next we're going to check the snapshot ID. And, well, these don't match. So this tells us that we haven't read the derived state of in this snapshot yet. But maybe we still don't have to recalculate it. We're going to go through the dependencies and see if they all match. So we're still seeing record 1 from state 1. Cool. So that can't have changed yet. We're going to check state 2. Also, same record. Great. So none of the dependencies changed, which means that there's no way that the calculation result could have changed. So we don't have to rerun the calculation. What we are going to do first, though, is update the metadata to say, all right, this snapshot's good. The next time you read from me, you don't even have to check the dependencies, because I've already validated that they're up to date. Then we're going to return the value and print it out. Now, let's do that again and watch the cache in action. So we're going to check, okay, we have a value, we've calculated it before. We're going to check the current snapshot. Snapshot IDs match. All right, cool. We've read the derived state before in this snapshot. We're going to check the write count. And this tells us, because these match, that no writes have occurred in this snapshot since we last checked, which means nothing could have changed, which means we don't even have to go through the dependency list. If you have a derived state that's reading tons of states, that can be kind of expensive. We don't even have to do that now because we know that it's already up to date in the current snapshot. The metadata is all up to date, so all we have to do is return the value and print it out. This is like the fastest path. All right, now we're going to do it right. We're going to see that the current record for state 1 doesn't match the current snapshot ID. That means we have to create a new record to write into. So we're going to give that record ID the current snapshot. We're going to write the value in. And we're going to increment the write count. And we're done. We're going to do that again for state 2. Create a new record. Give it the ID of the current snapshot. Write the value into that record. And increment the write count. All right. Now, back to the derived. Let's read it again. We have a value. Cool. Snapshot, same snapshot. Cool. Write count. Oh, all right. Some writes have occurred since we last checked the cache. So something might have changed. Now, this is possible that some other state was written to that the derived state of didn't read. So we have to go through the dependencies and see if our dependencies is what changed. So we're going to look at state 1 and see that, all right, the last time we calculated the value, we looked at record 1. But now we're seeing record 3. Remember from the when I was talking about how snapshots work, when you look at a state object, you look at the ID that's less than or equal to the current snapshot ID. And so we're going to see record 3 here. And that doesn't match record 1. So we know that state 1 has been written to since the last time we calculated the derived state of. So, all right, we've tried really hard, but we have to rerun the calculation. We're going to do that. That's going to give us the same value. OK, cool. So, well, all right. Let's update the metadata to say that actually the cache is up to date, even though the state's changed. When we do this, we're going to say the record IDs are newer, but they're still fine. And we're going to advance the snapshot again. And update the metadata in the cache so we can hit all those nice fast paths next time. And then we're going to return the value. All right. Last case. Now we're going to change a state to make the result different. We're going to check if we can write into the current record for state 1 again. Well, we have record 3. Snapshot ID is 4. That doesn't match. So we have to create a new record. So we're going to add a third record to state 1. Initialize it with the ID of the current snapshot. Take the value 42, write it in there, and increment the write count. Now we're going to read derived one more time. It's got a value. Great. Snapshot ID matches. Great. Write count doesn't match. So something's changed again. All right, we got to go through the dependencies. Going to check state 1. OK. State 1 changed. Got to rerun the calculation. We're going to rerun the calculation, and this time we're going to see we have a different calculation result. OK. Things just got real. So we're going to write this into derived state again, and we're going to create a new record here. And the reason we need a new record is because the value is changing. So the reason we can't write this into record 1 is actually because of nested derived states. So I didn't have time to show this example here, but if you have a derived state that reads another derived state, the first one is going to record that second derived state's record as well, and use that to check if it's changed. So in order to tell reading derived states that, oh, I actually changed my value, we have to create a new record, a new state record. So we're going to create a new record, all the same fields. We're going to initialize it with the ID of the current snapshot, the current records of the dependencies, and then put the cache value in there. Then we're going to advance the snapshot one more time, just burning through snapshot IDs here. Going to write that into the metadata, and then we're done. We can return the cache value. And now we've got a derived state of, well, it actually has 2 records. So if we get back into like the previous code snippet before we entered this with mutable snapshot, if we call that print derived value again, it would still see the cached 0 value from record 1 here. So the whole derived state of caching mechanism works in different snapshots independently, which is kind of cool. Wow. Okay, that was a lot of slides with animations to walk through. If that seemed really complicated, this is why you don't use derived_state_of for simple calculations like state 1 plus state 2. You're doing tons of work. You have all this bookkeeping you're doing just to try to save really no work at all. So this caching logic, it's so complicated because it has to handle like kind of 5 separate cases, at least. When it's read for the first time in a given snapshot, and no dependencies have changed. It's read for the first time in a snapshot, and some dependencies have changed. After it's been read already in the snapshot, but nothing has changed in that snapshot, or maybe something has changed in that snapshot. And it has to handle the case where you're reading a derived state that reads another derived state ad infinitum. All right, so some important things to note about derived state here. The calculation function must be pure relative to snapshot state. So the calculation function should only be reading snapshot state objects. It shouldn't be reading regular vars or class fields or whatever that aren't backed by snapshot state. And the reason for that is it uses the snapshot metadata to figure out if something's changed or not. So if you're reading something that's changed that's not backed by snapshot state, the whole cache mechanism has no way to tell that something's different, and it'll skip rerunning the calculation, even though it might need to. So only read snapshot states or constants in the calculation function. The other thing is, in this example, I showed basically the derived state of keeping a map of all the state dependencies to the derived state that read them. That doesn't actually happen in the implementation. Really what it does is just hashes all of the record IDs together. And it hashes the record IDs, not the actual values. So even if you're storing something in a state object that has an expensive hash code or whatever, you're not hashing that. You're just hashing the record IDs. And this is good enough because we don't actually care, derived_state_of doesn't actually care what the record IDs are. It just needs to know when they change. All right, we made it through. So there's 2 parts to derived_state_of, 2 functionalities. First of all, it dedupes invalidations. And it does this by coordinating with invalidation scopes. And the invalidation scope is actually what does the calculation to figure out if it needs to reinvalidate or not. And this feature takes advantage of caching because if it thinks something might have changed, it has to ask the derived state for its value again to compare with what it saw last time. If it hasn't changed at all, we'll hit the cache fast path and not rerun the calculation lambda. And the second thing is this caching, which uses snapshot metadata, and it can figure out, in most cases, it doesn't even need to rerun the calculation function to know that it hasn't changed value. And it uses state records to store all this metadata in. So again, use derived_state_of, reduce invalidations when your inputs change much more frequently than your outputs, or to cache expensive calculations that might not need to be used right away. Don't use it if the calculation is cheap and the inputs change almost as frequently as the outputs. So, a little homework. At some point after this talk next week, go to your code bases, try to find some derived state that's used incorrectly or doesn't need to be there at all, and take it out. All right, so that's the talk. Thank you for coming, and yeah.